Welcome to ChemCloud. Let's learn chemistry. So here in this video we will discuss about electrophilic aromatic substitution reactions. So in this video we will discuss only about examples of electrophilic aromatic substitution and general mechanism. So when we say electrophilic aromatic substitution reactions, so we'll just try to get a difference between addition and substitution. Here cyclohexene is reacting with bromine. So in this reaction, this bromine will get added across this double bond and we will get dibromo compound. So this type of reactions are called addition reaction. This is addition of bromine across double bond. And if you take the second example, where instead of cyclohexene we have used benzene. So benzene is aromatic compound, so it will not prefer to undergo addition reaction, it will rather undergo substitution reactions. So here you can see, in case of benzene we are getting monobromobenzene. Bromobenzene is the product. So here on the benzene we have one H on this carbon, so this H has substituted with this bromine, so this is called substitution reaction, right? Here are some examples of this electrophilic aromatic substitution reactions. So you can see this benzene is converted into nitrobenzene, so we call this as a nitration reaction. Second, benzene is converted into benzene sulfonic acid, so we call this as a sulfonation reaction. Third, we have converted that into bromobenzene, so this we can call bromination or halogenation reaction. Then we can perform alkylation reaction. This is well known as a Friedel-Crafts alkylation and Friedel-Crafts acylation reaction. So these are common examples of electrophilic aromatic substitution reactions. So first reaction for nitration, we use nitric acid, concentrate nitric acid HNO3 and concentrate sulfuric acid H2SO4 as a reagent. This is called nitrating mixture, right? For sulfonation we use concentrate sulfuric acid, concentrate H2SO4, or we can use oleum. Oleum is mixture of SO3 in H2SO4, SO3 in H2SO4, right? For bromination we can simply use bromine in acetic acid. Bromine is a stronger reagent, so we can use bromine in acetic acid. For chlorination, if you are going, then chlorine we can use in presence of some Lewis acid, say chlorine in presence of AlCl3, right? For alkylation we can use alkyl halide or CH2X in presence of AlCl3, Lewis acid. And for acylation you can use either acid chloride, so here I'm writing CH3COCl. Either you can use acid halide or acid chloride, or anhydride CH3COOCH3. Either you can use acid halide or anhydride in presence of AlCl3, right? So when we perform nitration reaction from this nitric acid and H2SO4, it will generate nitronium ion as intermediate, and double bond O positive charge, right? In case of sulfonation it will generate sulfonium ion SO3H plus, sulfonium ion. When we are performing halogenation reaction or bromination reaction, it will generate bromonium ion, right? Br plus it will generate. In case of alkylation it will generate carbocation, this R CH2 plus carbocation. And for acylation, when you are performing, it will generate acyl cation CH3CO plus, right? So these are the intermediates or electrophile which will be generated in the reaction. Now we'll see general mechanism for the reaction. So this is E plus we have taken the electrophile which are generated from those reagents which we are using. So this electrophile will react with the benzene. So one of the double bond of this benzene ring will attack on this electrophile, right? So one of the carbon will form bond with E. So you can imagine this double bond electrons are shifted toward one carbon, so it will get negative charge, and the other carbon should get positive charge, right? So this negative charge carbon is forming bond with E, right? So you can see this carbon has formed bond with E. On other carbon we should get positive charge, and on this carbon this H is already present, so that H we have shown here, right? Okay, so this intermediate is also called as sigma complex, sigma complex, right? Now in the next step, this H will give electrons here to form double bond, so benzene ring will get its aromatic character, right? And this H will eliminate as H plus, so we'll get substituted benzene, will get substituted benzene. So this is a simple mechanism for electrophilic aromatic substitution reaction. For this sigma complex which we have written here, for that we can write three resonating structures which we will write here. So this first structure I am writing as such. So we have two double bonds in the ring, then positive charge on one carbon, and this E electrophile, and this H attached to other carbon. So this double bond will shift toward this positive charge, and positive charge will come on this carbon, particular carbon. So we'll write that structure here. So we'll get positive charge on this carbon, we'll get double bond here. This is your electrophile and H, and this double bond will remain as such. Now this double bond will shift here and we'll get positive charge on this carbon. So we'll write this structure, right? So this double bond will remain as such. This is a new double bond. Here you will get positive charge. This is E and this is H. So if you compare with this original structure where we have a positive charge on this, so we have positive charge we have shifted on alternate carbons. We have shifted on alternate carbons. So we can write these three resonating structures for this sigma complex, right? Thank you.